What's up? Alan here again. Trig equations, part two. So we're going to see a little bit different type of trig equation. Um, some similarities, but I'll show you some of the key parts that make this different, which requires an entire new section. So here we go. First, just wanted to kind of talk you through a few things of how this section is different, and then we'll jump right into a few examples, and that's it. And you guys can practice and hopefully comprehend everything that we've been doing through this first couple of sections here in solving trig equations. So you can see a couple things here that are going to be different than what we've been dealing with. These equations are going to vary in the fact that they're going to have multiples of angles rather than just x or theta as our angle, and whether they had one trig function or a quadratic form with them squared or just multiple trig functions. Um, Still may have that situation occur, but and the big difference in this section compared to the last was there's going to be multiples at our angles. And hopefully you guys remember what that does, because we just had a couple of chapters ago an in-depth look, excuse me, of what an in-depth look of what our functions look like graphically. And so if we have a multiple at an angle, I wanted to give you guys some examples here. You can see that if I have just cosine x, and if I had cosine x is equal to 0, that was my equation, then you could see it would cross at two different parts in particular on this graph. And we should all know where those are located, right? At pi over 2 and 3 pi over 2. And so at those places, you can see there's two different instances where I'd actually be having to rewrite where my function is equal to 0. Two solutions, if you will. Now, if I took that away and I looked at cosine of 1/2 times x, hopefully you remember what that did to our graph. Remember, x's want the opposite of this. That's why they're called x's, right? So instead of multiplying by 1/2, we're going to divide by 1/2, which ultimately means we're going to end up multiplying by 2. And so our period will have changed, right? Our period will have changed to 4 pi, which means it will be elongated. And if I'm still looking from 0 to 2 pi, which remember is just over 6, then you can see I would only have one solution from 0 to 2 pi in one full circle, one revolution. And what would happen, do you think, if I put, instead of 1/2 in front of my x, my angle, what if I put 3 times the x? Well, we know when we just have x for cosine, we had two answers because there's two positive cases, two negative cases for every trig function. The only times that it's a little weird is at the quadrantal angles. And in this case, when we're looking for 0, there are two places where cosine is equal to 0. But when we multiplied by 1/2, we notice that our period would have been elongated. So when we're still looking from the same interval from 0 to 2 pi, now we'd have half as many answers. So you can imagine what would happen for my period when it becomes 3x. Instead of 2 pi, remember it would be 2 pi over 3. And so we would have 3 times as many zeros, x-intercepts, or solutions to this equation. And you can see 1, 2, 3, 4, 5, 6 different places that it will actually cross through the x-axis. And so what we're going to be doing is the algebraic version of all of that. And so when they ask us to find or solve the equations that have the multiples in them, you can utilize the fact that you know how that changes on our graph and how many different solutions that you should be coming up with, unless it's one of those special that ends up on the quadrantal angles. So without further ado, whether it's from 0 to 360 and using theta, or 0 to 2 pi and using x for our real numbers, and they're not always just going to be equal to something where the trig function is by itself. So you can see in part A, we still have that scenario where we have a trig function of some angle equals a number. But then in part B, you can see we also have cosine or some trig function of an angle, but this time it's a little bit different in that it's 2 times that. So starting with example 2a here, I'm looking for cotangent of what angle gives me root 3. Don't worry too much that it is 3x right now. We'll worry about that later. But just focus on the fact that you should know that cotangent of some angle is equal to root 3 when. And again, if you don't remember cotangent, that's all right. Just change it to tangent. But if you do that, then you're going to have to do the reciprocal of the right side as well, which would be root 3 over 3. So however you look at it, you need to be able to tell me what angle for tangent gives me root 3 over 3, or cotangent gives me root 3. And in that case, you should know that our angle, even though it's 3x in this case, for tangent that gives me root 3 over 3 is 30 degrees. But because we're dealing with real numbers like x and radians, we need to give them 30 degrees, which is pi over 6. Now don't forget, we're dealing with tangent and cotangent and a positive value. And since it's positive, we know we're not in quadrant 2 and we are not in quadrant 4. So we're looking at 1 and 3 this time. And we've now got our reference angle. So we're also going to have to take that angle, which we had 3x, and we're going to have to set it equal to, well, if pi is right here, then since it's pi over 6 as our reference angle, I'm going to multiply it by a 1 of 6 over 6. Because all I'm going to have to do is add a pi over 6 to get 7 pi over 6. However, from looking at our trig function of cosine 3x, we know that there should be 1, 2, 3, 4, 5, 6 possible answers. Right now, we only have 2. So what did we say that we could always do to get a same ratio out, but at a different angle? That's right. We said that we could add 360 degrees or 2 pi. So in this case, I'm going to add 2 pi as many times as I need to in times. Now you can probably guess how many times I'm going to have to do this. Because there is a 3 there, I know I'm going to have 3 times as many answers as I normally would, which typically is 2, unless we're on a quadrantal angle. There's 2 positive, 2 negative for every trig function. So in this case, I'm going to have to take, for this, we're going to call it n, the number of times, and it's always going to be 1 less than whatever it is, starting at 0. And we say we start at 0 simply because we don't need the first one. We don't need the first 2 pi or 360 rotation around because we already have that first angle of pi over 6. So in order to do this, I'm going to have to do a couple of things. One, I need a common denominator. So I'm going to put all this over 1, and then I'm going to do the same thing over here. I'm going to multiply this by my funny looking 1, which in this case would be 6 over 6. So my first answer for this, which again, I haven't technically solved for it yet, but this is how they're all going to look. This one's going to be pi over 6 plus, this becomes 12 pi over 6 n times. Now again, hopefully you can see the way that I've written it. 12 pi over 6 is still 2 pi, or 360 degrees, one rotation, revolution around. So now I have 3x equals pi over 6 plus 12 pi over 6 n times. And this is what I'm going to use to find all of my answers for quadrant 1. Now I'm going to do the same thing over here for quadrant 2. I'll have 3x equals, this time my reference angle is 7 pi over 6. And when I add that 12 pi over 6 to it n times, that will give me my other answers. So I will now do 3 different steps in order to give all possible solutions within 0 to 2 pi, the interval that they gave me. The easiest is the first. I will let n equal 0. And when n is 0, that means I get 3x equals pi over 6 plus 0. Now, if you want, you got options here. If you don't want to have to divide by 3 every time to these, you can do one more step. And let me show you that as well, just in case you prefer this method, because it is a little bit faster. You could take this and multiply by 1/3 to every single one of these as well. So if I do that, I now have x all by itself. And even though on this part I could cancel the 3 with the 12, I'm not going to because I need a common denominator. So I'm actually going to leave it as 12 pi over 18 n times. And this is actually the equation that I would use rather than the one in orange, because remember, our goal is to get x by itself, and now we've got it. So I'm going to do the same thing over here. I'm going to multiply by that 1/3 to divide by 3 to every single one of my parts of my equation, and then that will give me my x for the second solution. And then I'll go ahead and plug in my 0, 1, and 2 for all three scenarios that we should be finding on this particular graph. But we found them exactly by doing what we've done algebraically. So to finish up, I'll let n equal 0 for both of these. I'll let n equal 1 for both of these, and then I will let n equal 2. It's always going to be whatever the multiple is minus 1, starting with none, because we don't need a revolution. We don't need a same point. So in this case, if I add 0, I just get pi over 18 for x. This one over here, 7 pi over 18. But for this one, I'm going to have to take the pi over 18 and then add 1 revolution, which we rewrote it by 12 pi over 6. And then we multiply by that 1/3 to get 12 pi over 18. Now, again, I know that can be simplified and reduced, but I need a common denominator, so I'm just going to keep it. And not only do I do it once, I can also do it over here a second time. And when I double that, instead of 12 pi over 18s, I would have 24 pi over 18. And so my other two answers for the original pi over 18 would be 13 pi and 25 pi. And if I do the same thing over here to the 7 pi over 18 and add 1 of my 12 pi, and then add a second, which again would be 24, I'll get my other two solutions, which would be 19 pi over 18 and 31 pi over 18. And so to write my final answers all in order, the way that you would see them on a test quiz, if it was multiple choice, you would say my solution set from smallest to biggest. And don't forget, they asked us to find everything between 0 and 2 pi. And to make sure that all of these are, remember 2 pi with the denominator of 18, I'd have to multiply by that fancy one, and I'd get 36 pi over 18. That's what's equal to 2 pi. And you can see we're definitely less than that. So we actually got 6 answers for this particular one. And again, we should have known that because it was 3 times the x.